Eureka!
The story so far. Molecules are made up of atoms, and atoms are made up of a nucleus and varying numbers of electrons. The nucleus is a little speck of matter right in the middle of the atom, and the electrons are even tinier specks of matter which whiz round and round so fast that they appear to form a shell round the atom. And now, conduction.
If you stir a boiling liquid with a plastic ladle, after a few moments, the ladle will become quite warm. The same will happen with a wooden ladle. And a ladle made of metal can even become too hot to handle. This is because the heat from the boiling liquid is able to travel up the length of the three ladles, quite slowly through plastic and wood, and very fast through metal. But how does heat manage to do this? How does heat travel through things? Well, when the hot liquid heats up the end of each ladle, its molecules, or in the case of metal, its individual atoms, start to vibrate more rapidly. And when the heated molecules, or heated atoms, vibrate faster, they start bumping faster and faster into their slower neighbors, causing them to speed up in turn, and bump into their neighbors, and so on all along the ladle. In this way, the increased speed of vibration, and therefore the heat, is passed on from molecule to molecule, or from atom to atom. It's like a row of dominoes knocking each other over. And this domino effect, which leads or conducts heat through any substance, is called, naturally enough, conduction. Non-metals, such as wood and plastic, conduct heat quite slowly. They are bad conductors of heat. In contrast, all metals conduct heat very rapidly. They are good conductors of heat. That's why the witch with the metal ladle got burned. But why is heat conducted so much faster through metals than through non-metals? Why are metals good conductors? What's their secret? Well, the secret lies in the fact that there's something very peculiar about the atoms in metals. We know that all atoms consist of a nucleus with a number of electrons whizzing around it, as in this very simple model. And we also know that the nucleus exerts a force of attraction on these electrons to make sure that they don't go wandering off all over the place. But if it were possible to look very closely at a group of atoms in the metal ladle, we'd see something like this. There are a lot of electrons that don't seem to be attracted to any nucleus. They're shooting about extremely rapidly in all directions. It's like this in all metals, in fact. They all have these free electrons, which are quite independent of the atoms themselves. Now look at what effect free electrons have when the end of the metal ladle starts to get hot. Not only do the atoms start to vibrate faster, but the free electrons also speed up and begin to move faster still, colliding with the atoms more and more often and with more and more force. And each time a free electron bounces off an atom, it causes that atom to vibrate a little faster. Imagine that the atoms were pins in a pinball machine, and that each of the free electrons were one of the pinballs. Each time a pinball hits a pin, the pin lights up, just like an atom vibrating faster. And the more rapidly the pinball moves, the harder and more often it bounces against the pins. If you could fire dozens of pinballs simultaneously, you'd be lighting up the pins like crazy. You'd be producing the same sort of effect that occurs when the metal ladle is heated. Only in the case of metal, of course, there are millions and millions of free electrons to speed up the vibrations of the atoms, and therefore speed up the spread of heat. And that's the secret of why metals are such good conductors. Much better than plastic or wood.